Here is example 3. Again, you see this word rigid. A rigid bar ABCD is supported by 2 bars, bar 1 and bar 2, is shown in the figure. So there is no strain in the vertical bar before load P is applied. After load P is applied, the normal strain in bar 1 is 570 micrometer per meter. What does this mean? This is micro strain, right? So this is just micro strain. Assume A, B, C, L1, L2, those dimensions have been given. Determine the normal strain in bar 2. And also the normal strain in bar 2 if there is a gap in the connection at pin C before load is applied, or a gap in the connection at pin B. Right, these are 3 questions. Let's look at the first one first. Right, this is the normal strain in bar 2. We look at this system, this structure. We said this ABCD bar is rigid. So what does that mean, rigid? We mentioned that before. Rigid meaning that this bar will not be stretched, will not be compressed, will not be bended. It will not deform at all. It always keeps straight. But in this case, since it's pinned to point A, right? So when you add a P at a point D, this rigid bar ABCD can only be rotated about point A. Okay, it can only be rotated at point A. So this will be rotated like a to a position like this. Right? So this is what does this condition mean, the rigid. And the second condition, apart from the dimensions, we only know that the bar 1, the normal strain of bar 1, normal strain of bar 1 is 570 microstrain. This is the only condition we know. Right? This, how can we find the normal strain of bar 2? Right? So we're finding normal strain of bar 2. Right? Obviously, if you want to know epsilon 2, you should know delta 2 first. And delta 2 over L2, you get the epsilon 2, right? Then we know L2 already, but we don't know delta 2. So how can we find delta 2? Since we only know, apart from the ABCD is rigid, we only know that the epsilon 1 is 570 microstrain, right? This is the only known. So based on this, we can calculate the delta 1, right? Based on this, we can calculate delta 1, and we can find a correlation between delta 2 and delta 1, right? So that we can solve delta 2. Right? If we solve the delta 2, then we can calculate epsilon 2. Right? So this is the overall strategy to solve this problem. Then let's see in detail how to solve it, how to find the normal strain in bar 2. Okay, so first of all, let's look at so step A. Okay, in step A, we're looking for epsilon 2. This is the first condition. Based on the first condition, that the bar ABCD is rigid. Okay, ABCD is rigid. As we analyze, that means that this one will not be deformed, but it can only be rotated. Right? So after the rotation, after you add the P, right? So this bar ABCD, this is point A. When you add P, it will be rotated to this position, right? So we have point B here, point C here, and point D here. And after the rotation, you will get A, B prime, C prime, D prime. Okay. Okay. So in this triangle, so you can see the similar triangles here, like A, B, B prime, A, C, C prime. These two triangles are similar, right? So we can find a correlation. We can find a correlation here, like based on the condition of A, B, C, D is rigid, right? Since we have know that the AB is A and BC is B, right? So we can find the correlations between delta B. So here is delta B, the displacement of point B, and the displacement of point C, delta C. Right? So what is the correlation between delta B and delta C? So here we can write this correlation of these two things. That will be delta B over A equals delta C over what? A plus B. Right? So this is our first equation. This is our first equation. Since we're not calculating delta B, delta C, those are the displacement of those points B and C on this rigid bar A, B, C, D. Right? We're calculating the deformations and the strains of bar 1 and bar 2. Right? So we also need to find the correlations between the bar deformations and the point displacement. Right? Since the bar 1 is tied to is connected to this rigid bar at point B, and bar 2 is tied to this rigid bar at point C. So we can know that in this situation, the deformation of bar 1, the deformation of bar 1, right, the length change of bar 1, delta 1 always equals displacement of point B. And the deformation or the length change of bar 2 always equal to the displacement of point C, delta C. Right? So this is our second equation, second set of equation. Okay. So based on these two sets of equations, we can get the correlation between delta 1 and delta 2, right? Just substitute the two equations in 2 to equation 1. So we will get we will get delta 1. Let's use another color. We'll use delta 1 over A equals delta 2 over A plus B. Right? So do we know delta 1? We don't know delta 1, but we know what we know epsilon 1. Right? So delta 1 here equals epsilon 1 times L1. Right? Epsilon 1 has been given. Epsilon 1 here 570 microstrain times L1. L1 is 900 millimeter. So this will be 0.513 millimeter. Okay. Is this positive or negative? So when you add the P downward, this bar 1 will be compressed, right? So this thing is actually a negative value, right? This is a negative value, but we will not use the signs in this calculation since it's just a geometry. We're calculating everything based on geometry. So the negative sign, positive sign doesn't matter. You just know the values, the magnitude of those deformations, right? But you should know what this is in compression, and the other bar 2 will be in tension, right? So the deformations of bar 2 will be positive, right? So here we have no delta 1, right? So we can calculate delta 2, right? So the delta 2 from here and from there, we can calculate the delta 2. And that will be 0.513 This is delta 1 times A plus B over A, right? So A plus B will be 240 plus 360 over 240. Right? So this will be 1.283 millimeter. Okay, so based on this delta 2, we can calculate epsilon 2, right? So epsilon 2 will be delta 2 over L2. 1.283 over L2 is here, 1,500. Well, that would be 855 microstrain. Is this positive or negative? As we just mentioned, this will be positive. Right? Then how about step B? Let's look at step B. The same question was normal strain in bar 2. Right? We're also calculating normal strain in bar 2. But if there is a 1 millimeter gap in the connection at pin C before the load is applied, okay, pin C is here, pin C is here, right? So what does this gap mean? This is illustrated here, meaning that you have a gap between this pin at point C and the bar, and the edge of the hole on the bar 2. Okay, meaning that when you add load P, the rigid bar A, B, C, D have to travel for 1 millimeter first before it can touch the edge of the hole on the bar 2. Okay, clear? Clear about the meaning? That means this pin at point C has to travel for 1 millimeter before it touches the bar 2, right? Meaning that the displacement of point C will always be 1 millimeter larger than the deformation of bar 2, right? So let's summarize this analysis using an equation. That is what? That is delta C always equal delta 2 plus 1 millimeter. Okay, so since we didn't say that there is a hole at point B, right? So the other equation in here will still be the same, right? So delta B equals delta 1. And the equation 1 here will not be changed since we established this equation based on the assumption of rigid ABCD bar, right? So the first equation will not be changed. So all of this analysis in step A will not be changed apart from one equation in equation set 2. Right? We have written it here. Right? So this is the only change happened to the whole analysis because of a 1 millimeter gap in the connection at point B, at point C, right? So based on this analysis, we can write the equation to solve the epsilon 2, right? So we just start from here, start from this equation. Well, we need to rewrite this equation to delta 1 over A equals what? The delta 2 will be replaced by delta 2 plus 1, right? So we get delta 2 plus 1 over A plus B, right? Since the delta 1 will still be the same, right? So delta 1 will still be the same. delta 1 will still be the same, so we have derived that in the step A. Delta 2 equals 1.283. So here in this equation, we should have a condition that delta 2 plus 1 equals 1.283. Right? So from here, we can derive that delta 2 equals 0.283 millimeter. And then how about epsilon 2? That will be 0.283 over 1,500. This will be 188.7 microstrain. And then step C. Step C, again, we just calculate the epsilon 2. But the condition has been changed. So this time in step C, we don't have any gap at the point C. We have a gap at the point B. But again, this means that when you add the load P to it, this bar, this pin at the point B will have to travel for 1 millimeter before it touches the edge of the hole on bar 1. Okay, so again, the equation 1 will not be changed. So one of the two equations in equation set 2 will be changed. So this time it will be the first one, will be this one, right? This one will be rewritten as delta B equals delta 1 plus 1. Since delta B will always be larger, since I just mentioned point B will always travel for 1 millimeter before it touches the edge of the hole to make any deformation to bar 1. Okay, so the different equation will be delta B equals delta 1 plus 1. Now the other one, the other equation in the second set of equations will be the same. And it will be delta C equals delta 2. Okay, so the equation, again, this equation will be rewritten as, so this time it's delta 1 plus 1 over A equals delta 2 over A plus B, right? So we'll just get this equation that would be delta 1 plus 1 over A equals delta 2 over A plus B. So we have known that the delta 1 is 0.513. This will not be changed, right? So 0.513 plus 1 over A, that is 240, equals delta 2 over 240 plus 360. Then we can derive that delta 2 equals 3.7825 millimeter. Okay, this time the result will be larger, will be much larger, right? This will be 3.7825 over 1,500. Okay, this will be 2,522 microstrain. So you can see the differences. Just when you have a gap, we just need to analyze what are the conditions will be changed. What conditions will be changed? Okay, just when you have this rigid bar, when you have a hole on the non-rigid bar, deformable bar, this point, this pinpoint at the rigid bar will have to travel for the distance of the gap before it touches the deformable bar. Okay, so the point displacement will always be larger than the deformable bar. Okay, this is the core the key point to understand this type of problems, this type of problems with gaps. Okay, you will see more examples later regarding the gaps. Gaps because of a hole and the gaps between two elements, right, etc.